watching this video is an encouraging sign, because that tells me you survived the product of quotient rule and the chain rule. And if you did indeed survive the product of quotient rule and chain rule, well, I think you're going to find this lesson a cinch. We don't need the product or quotient rule to get the derivative here. We can simply use the power rule on each of these terms. Of course, 4 times 1/2 is 2, so the derivative here is 2x to the third. The derivative here is 6x squared. We know the derivative here is negative 12x. The derivative of 3x is 3, and we can use our constant rule. The derivative of negative 5 is, of course, 0. This is the derivative, or we could specify the first derivative of f of x. Well, we're here today to learn that there's something in calculus known as a second derivative, and it's nothing more than a derivative of the derivative. So let's see what the second derivative of f of x is. The derivative of 2x cubed is 6x squared. The derivative of 6x squared is 12x. The derivative of negative 12x is negative 12. And of course, the derivative of 3 is 0. Now, after today's lesson, we'll probably never encounter one of these again, but we even have something called a third derivative. And of course, the third derivative is just the derivative of the second derivative. So the derivative of 6x squared would be 12x. The derivative of positive 12x is positive 12. And the derivative of negative 12 is 0. I've seen the notation for a fourth derivative expressed a few different ways, either with 4 primes or a 4 in parentheses. And of course, the fourth derivative is just the derivative of the third derivative. And the derivative of 12x is 12, and the derivative of 12 is 0. Of course, the fifth derivative would be the derivative of the fourth derivative. The fifth derivative would be 0. And I suppose the sixth derivative would be 0, the seventh derivative would be 0, and so on and so forth. In number 2, we have a function that we could differentiate using the quotient rule, but I'll give you a good rule of thumb. Never use the quotient rule if either the numerator or denominator is a constant. And notice, we have a constant in the numerator. If we were to use the quotient rule, we would start by putting the bottom times the derivative of the top, and the derivative of the top is 0. That's an indication that there should be a better way to do this. I'm going to instead rewrite this equation. I'm going to move this x plus 3 up to the numerator and change its exponent to negative 2. And now please notice that we're not going to need to use the product rule because we have a constant multiplier. So to find our dy dx, I'll just use the chain rule, or what we sometimes refer to as the general power rule. Let me move the negative 2 into the front, so it would be negative 10 x plus 3. I'll subtract 1 from the exponent, so this will become negative 3. And then I need to multiply by the derivative of x plus 3. And what do you know? The derivative of x plus 3 is just 1. Here's our first derivative. Perhaps I'll rewrite it with positive exponents. Before I continue, let me point out to you that if this were not a 5, if this were, say, x, if this were x, I would not want to rewrite it this way, because getting the derivative here would require the product rule. You should never use the product rule when you could just use the quotient rule instead. I know you may think the quotient rule is a little bit more complicated, but the product rule becomes much more complicated with a negative exponent. But anyway, it wasn't an x, it was a 5, and using the chain rule is a cinch with a negative exponent. If our first derivative is notated in dy dx form, then this is the way we indicate a second derivative. I know it looks kind of weird with the 2 here and the 2 here, but I'm sure if you see this again, you'll recognize it. All right, of course, to get the second derivative, we're going to get the derivative of the first derivative. If we used it in this form, we would need the quotient rule. I think it's going to be much easier to use the chain rule with this negative exponent. So my second derivative would be negative 3 times negative 10, or 30, and then x plus 3, I'll subtract 1 from the exponent, so negative 3 minus 1 is negative 4, and then of course the derivative of x plus 3, once again, is 1. After today's lesson, we won't be encountering any more third derivatives this year, but I do want you to know that there is something known as a third derivative. And of course the third derivative is just the derivative of the second derivative. So negative 4 times 30 is negative 120, and then x plus 3, I'll subtract 1 from the exponent to make it negative 5, and the derivative of x plus 3 is still 1. So I suppose this would be a more proper way to represent the third derivative. Now, in first semester calculus, we don't use third and fourth or fifth derivatives very often, but we do use first derivatives and second derivatives quite a bit. Here's a fun example. I know the derivative of sine x is cosine x. And of course, the derivative of cosine x is negative sine x. Well, when I get the derivative of negative sine x, this negative is a constant multiplier, and the derivative of sine x is cosine x. When I get the derivative of negative cosine x, this negative is a constant multiplier, and the derivative of cosine x is negative sine x. And of course, a negative sine x is a positive sine x. And we of course know the derivative of sine x is cosine x. If we keep differentiating this function, we'll get caught in an infinite loop of sines and cosines. Here in example number 4, I'm being asked to find the second derivative if y equals sine cubed of 2x. Well, of course, before I find the second derivative, I'm going to need to get the first derivative. And we saw in our prior lesson, to get the derivative of something like this, it's a wise idea to rewrite it as sine of 2x all to the power of 3. Now to get the derivative, we can use the chain rule, or what we sometimes refer to as the general power rule, because we have something raised to a power. So I'll of course move the 3 in front, and then sine of 2x, I'll raise it to only the power of 2, but then I have to multiply by the derivative of sine of 2x. I know the derivative of sine is cosine, so the derivative of sine of 2x is cosine 2x, but let me not forget, I need to also multiply that by the derivative of 2x. Let's see if we can neaten this up a bit. I have a 3 and a 2, so the coefficient is 6. I then have sine of 2x to the power of 2, or sine squared 2x. And finally, a cosine 2x. Well, now we're going to get our second derivative, which means we're of course going to be getting the derivative of this, and there's two different ways we can think of this. We're going to need to use the product rule. We can think of the first function as 6 sine squared 2x, and the second function as cosine 2x. Or we can think of this 6 as a constant multiplier, and then just use the product rule inside here and think of the first function as sine squared 2x, and the second function as cosine 2x. I think I'm going to take advantage of the fact that 6 is a constant multiplier. Let me just bring 6 along for the ride, and now I need to get the derivative of sine squared 2x times cosine 2x. Don't forget that sine squared 2x is sine of 2x to the power of 2. All right, let's go ahead and perform the product rule inside these brackets. I'm going to put the first times the derivative of the second. The first piece is the sine squared 2x, and then times the derivative of the second piece. Well, the derivative of cosine 2x is negative sine 2x times 2. Then I'm going to add the second piece times the derivative of the first piece. So the second piece is cosine 2x. And of course, to get the derivative of the first piece, I'm going to refer up here and use my general power rule. Let me put the 2 in the front. Then of course it will be sine of 2x to the power of 1. And then I have to multiply by the derivative of sine of 2x. And the derivative of sine of 2x is cosine of 2x times 2. Before I try to simplify this, let me highlight any addition or subtraction symbols. So please notice that there's only one. All of these things are multiplied together. So all of this can be expressed as one term, and all of this can be expressed as one term. So over here, I have a positive times a negative times a positive. I know it's going to be negative. I know the coefficient is going to be this 2. So I've accounted for this negative, and I've accounted for this 2. And notice I have sine squared of 2x times sine of 2x. Well, that's going to give me sine to the third of 2x. Then I'll put my addition symbol, and over here I have something times something times something times something times something. I see they're all positive, and the coefficients I see are 2 and another 2. So of course 2 times 2 is 4. I've accounted for this 2 and this 2. I have a cosine 2x and another cosine 2x. That would be cosine squared 2x. And finally, I have a sine of 2x. I already have a 6 factored out. Perhaps I could also factor out a negative 2, and perhaps I could factor out a sine 2x. So I pulled this negative 2 out, and I pulled out a sine 2x, so I'm left with a sine squared 2x. And if I pull a negative 2 out of here, I would have negative 2, and I pulled this sine of 2x out, I'll be left with this cosine squared 2x. So anyway, here are two different ways I could express the second derivative, and I suppose another way you could express it is to just distribute this 6. In this last example, we're being asked to evaluate f double prime of 3 when f of x equals the square root of 2x plus 3. We're of course going to need to get the second derivative. Before I start differentiating, I'm going to rewrite the square root of 2x plus 3 as 2x plus 3 to the 1/2. I'll use the chain rule, or general power rule, to get the first derivative. Let me move the 1/2 in the front, and then 2x plus 3, I'll subtract 1 from the exponent. 1/2 minus 1 is negative 1/2, and then I need to multiply by the derivative of 2x plus 3. I'll multiply by 2. Now, before we go get the second derivative, let's notice that we can simplify this first derivative. 1/2 times 2 is 1. So now I simply need to get the derivative of 2x plus 3 to the negative 1/2. I'll move my negative 1/2 in front, and then it will be 2x plus 3. When I subtract 1 from the exponent, negative 1/2 minus 1 is negative 3/2, and I of course need to multiply by the derivative of 2x plus 3. I'll multiply by 2. Now, before I attempt to evaluate f double prime of 3, it would be a wise idea to rewrite this without negative exponents. I'll put my negative in the numerator, I'll put my 1 in the numerator, and my 2 in the denominator, and my 2x plus 3 will go in the denominator because it has a negative exponent. But of course, instead of negative 3/2, I'll put positive 3/2. And finally, I'll put my times 2 in the numerator. Notice in the numerator, we have something times something, and in the denominator, we have something times something, which means it's legal to cross off these 2's. Or I suppose I could have just multiplied that 2 times negative 1/2 to get the negative 1. All right, I think we're finally ready to evaluate f double prime of 3. When I plug 3 in, 2 times 3 is 6, 6 plus 3 is 9, and 9 to the 3/2, well, we have a choice. We could do 9 to the power of 3 and then square root, but I think it would be easier to square root first. The square root of 9 is 3, and 3 to the power of 3 is 27. So I'm going to say f double prime of 3 is negative 1 over 27. All right, time to go get some practice getting your higher order derivative.